To start talking about easy problems, we're going to start with the shortest path problem. In the shortest path problem, we're going to be working with a slight variation on the graphs that we've been working with so far. In particular, we're going to be working with directed graphs. In a directed graph, we're given a set of nodes, v, but instead of edges, we're given a set of arcs. An arc now has a direction. That is, an arc moves from one vertex to another. This is in contrast to an undirected graph where an arc is just between two edges, for example here. We can encode an undirected graph, that is the graphs that we've been working with, by considering each edge and making it directed in both directions. That is, there's an arc moving from u to v and from v to u for every edge uv. With the shortest path problem, we're going to be working with only the arc version. We're not going to be talking about edges. In the shortest path problem, we're given as input a graph, which is a set of nodes and arcs. And keep in mind that these are directed arcs. We're also given a weight on every arc, WA. We're also given two nodes, a start node S and a termination node T. The objective is to find a path between S and T that minimizes the weight. So we'd like to find a path that goes between S and T, and the sum of the weights of the arcs between S and T that we use is going to have a minimal weight. Here we have a particular input, a particular graph, and the nodes S and T are marked. The edges on each arc are also denoted with these numbers. If we were to find the shortest path inside of this graph, we would first choose this edge, then we would choose this edge, then we would choose this edge, and finally we would choose this edge. Although for now you'll just have to trust me that this is the shortest path, I can assure you that it is. If we were to look for any other path, it would have either a larger value or a value that's at least this value. In this case, the value of the shortest path is equal to 7. So when we sum up the weights, sum over A and P of WA is equal to 7. We can formulate the shortest path problem as an integer program, but to do so we need a little bit of notation. The notation is going to be v plus of I and v minus of I. If you look at a particular node I, v minus of I is going to be defined by all the arcs going into I. And in particular, for any node in v minus of I, there's an arc from that node to I. V plus of I is the opposite, and it's defined by the arcs moving out of I. So in particular, for any node in v plus of I, there's an arc from I to that node. To write the integer program, we're first going to look at a particular path, a particular shortest path, to get an idea of what all these constraints are doing. These edges that I'm marking in pink are going to be the path that we're going to look at. And we can note that it's a feasible shortest path from S to T. It doesn't really matter what the weights are. To write the integer program, the objective function is straightforward. We want to minimize the sum of the weights among the arcs that we're going to choose. The first constraint has to deal with S, and it says that if we look at all the arcs in S, and we look at the arcs moving into S, that is, arcs in V minus of S, and then subtract out the arcs going out of S, that is, the arcs moving to V plus of S, that this sum has to be minus 1. In effect, this constraint is telling us that there has to be at least one arc moving out of S. And if there's an arc going into S, then there has to be an additional arc moving out of S. We won't deal with that second complication. The second constraint says the same thing about T. If we look at T, there's one arc that's moving into T. The second constraint says exactly that. It says that if we sum up the arcs that are moving into T, and we sum up the arcs that are moving out of T, that they sum to 1. This is exactly what we want. One arc moving into T, and if another arc moves into T, then another one has to move out. For every other arc, we have a so-called balance constraint. So if we look at a particular node, we'll note that the number of arcs moving into the node is the same as the number of arcs moving out of that node. This final constraint summarizes exactly this. It says that if we look at the arcs coming into the node, that is the arcs coming from V minus, and subtract the arcs going to V plus, that these arcs are going to cancel each other out and equal to 0. These are the only constraints we need for a shortest path. There's at least one arc moving out of S, there's at least one arc moving into T, and for every other node, for every arc moving in, there's an arc moving out. We have balance. Finally, we put these on the lattice. That is, all these xij's have to be equal to 0 or 1. This is the integer program formulation for the shortest path problem. In the next lecture, we're going to look at properties of this shortest path.